Okay, take 23. Let me see. This is the 23rd attempt at giving the review lecture on electromagnetism for second year students. You may find I'm rather relaxed by now because given that it's take 23, you can imagine that now I've got some coffee here. I'm just writing down the start time. If I'm successful this time, then it's going to be very late coffee. So let's give it a go. Let's see whether I head off into some direction or say something where I think to myself, man, I can't believe I said that. Yes, I think that's true, but I'm not allowed to say that in public. I certainly don't want a video recording of that. And not surprisingly, we're on take 23. So here we go. So this is it's so much better when you just give a live lecture. You guys can ask questions. We can have a bit of fun. Yeah. Anyway, that's where we are. Take 23, and let's get this act together. Okay, take 23. We're going to do a review lecture, and in the review lecture, we try and tie together some of those threads that we looked at in detail during the course, and try and make sure that we can see this whole body of work. Electromagnetism and Maxwell's equations. I mean, of course, other people teaching science are not going to admit to it, but we all know that this material is just some of the most beautiful physics you will ever do in your life. It inspired Einstein. It underpins, Feynman said, as you know, that there are 7 equations in all of classical physics, and Maxwell has got 4 of them. How can this not be some of the most beautiful science that we'll ever do in our lives? So there we are. That's what we're about to do. Oh God! So I'm looking outside. I'm aware there are some dark clouds that are passing over Britain at the moment, and I'm thinking of this incredible cathedral in Durham that's been here for 900 years, and you just think. We will all be determined to be the heroes of our own life, which means that in your case, I recommend you take your responsibility to do the best you can in these exams as seriously as you can, so that when you get to the end, you can sit around with the people that you love and the people that then say, look, I did the best I could with the strengths and weaknesses I had. It's not about attainment necessarily. It's all about achievement. So, yeah, that's where you want to be. You want to take care of the people around you. You want to, of course, you've got a big responsibility. So work hard between now and your exams. And when your exams are gone and your formal responsibilities somewhat diminished, then you might make a particular effort to try and seek out the vulnerable and those who really would benefit from your help. Anyway, there's going to be other people in the debate about what they think you should do. It's my job to show you, remind you and review this incredible material that we looked at. And of course, we're all reminded just how important the scientific community is at this time. How, we're a broad community. Of course, the focus now is on vaccines and doing the best we can in terms of sorting this CV-19 out in the short term, and then in the medium term, physicists normally, at least physicists in my area, work in the medium term on the time scale of maybe 10 years or something like that, where we need to make sure that we try and sort out the other issues that are also coming our way that the free market will not deal with very easily, such as global warming. All right, so we need some really great scientists. We need people who have trained their minds to think very clearly and accurately and objectively, so that when a politician says we were led by the science, you know really what that means, being led by the science, and you can assess whether they're really being led by the science or not, and you can understand that science has some aspects of it, like the material that we're going to look at, where there really are predictive answers provided from the science, and there are other areas where we have a number of scientists and we don't have a mathematical description in the way that we do with Maxwell's equations, and things become more complicated. So the irony of this course is that although it's one of the tough courses that you do in physics, actually there's something very beautiful and simple about it. Doesn't feel that way when you're doing it. Never felt that way for anyone who's done this course. Never felt that way when Einstein was sitting down and looking at Maxwell's equations, trying to come up with special relativity. So don't imagine that this isn't a tough course for everyone. Just do the best you can. So I need to give a health warning. Man, I've given this health warning more often than anyone should. First of all, I give it every year, and secondly, I've given it to this bloody video recorder. You know, at the beginning of this lecture course, I asked you to write to the VC saying, please, can we have some decent video lecture capture? Man, oh man. Please write again if you wrote. If you didn't write now. No, don't write now. Work hard for your exams. After your exams, write to the VC. Say you're one of the best of your generation in physics. You're at Durham. You're at one of the world's leading universities. And we need some decent video capture. So, yeah, okay. Yeah, he'll probably write to me telling me I shouldn't have asked you to do that because he knows it. But anyway, write anyway. Don't. We're British. Many of us are British. Many of us who are not British are here to see what the British do. And what the British do in difficult circumstances often is write a letter. All right. Okay. Health warning. Do not imagine that that I'm going to give you any idea of what's in the exam. I'm claiming that I've almost completely forgotten what's in the exam. So if I say that this is really important, that I think that time dilation or Lorentz contraction or waveguides or anything is really important, do not imagine that I'm telling you what's in the exam. I'm not. I'm saying those things because I think they are important and for no other reason. You can assume that I have not even written the exam. Okay, that's the first health warning. And the second is that you don't need, there's nothing new in this review lecture. There's all I'm going to do is look through the summary notes for the lectures that we posted months ago after each few lectures. So after we'd completed each theme, as you know, after typically 3 or 4 lectures, I would post a summary of the lectures. All I'm going to do is look through those there. So the only thing you might do is annotate your lecture notes or annotate your summary of lecture notes as we're going through, just with some comments. Okay, let's go. We're going to kick off. So this is the first lecture, and as you know, we wrote down Maxwell's equations in their most general form. We looked at equations 1 to you can see that 1.1 to 1.4. These are Maxwell's 4 equations, and you can see that on page 1 there's the 7 equations that Feynman tells us describe all of classical physics. So we've got F equals ma. We've got Newton's law of gravity. We've got the force on a charge in a magnetic field and an electric field. Those are the 3 of the 7 equations, and then the other 4 are Maxwell's equations. So, of course, Maxwell has this huge role in physics, having written down these four equations. And you can see in the fourth equation, the curl B equals mu naught J plus mu naught epsilon naught dE by dt, that the additional term, this term mu naught epsilon naught dE by dt, that Maxwell added, that couples up the E fields and the B fields and leads to electromagnetic waves. So these are the equations. They're written here in their most general form. And you know that basically what we spend our time doing when we go on to look at materials or look at any system is we just need to make sure that for the charge density in Maxwell 1 and the current density in Maxwell 4, we include all the currents and current density and charge density that occurs in the system. That allows us to calculate the E fields and B fields. And then we can work out the forces on all the charges and all the currents. And from there, we can see how the system evolves. So that's basically describes or explains why Maxwell's equations are so pervasive. Once we know the charges and the currents, we can calculate the fields. Once we know the fields, we can calculate the forces. And if we know the forces, we can calculate how things evolve. And Maxwell very much concentrated on the forces on these charges and current densities. Actually, he didn't write these equations down in their form that we see here. Heaviside wrote them down in this rather more elegant form, involving the divergence and the curl of the E field and the B field on the left-hand side of these four equations. Maxwell concentrated more on the forces because, of course, he was affected by Newton. And Newton was this huge figure in, and still is, this huge figure in physics that basically deals with the properties of objects and forces between objects, how they accelerate, how they collide, gravitational forces, and so on. And it was all a matter of calculating this mysterious but important thing called a force. And from there, you could see how systems evolved. And Maxwell did the same thing. He basically wrote his equations all down in terms of forces. What we do now is we write them down in terms of fields. So the charges and the currents generate fields, and then we calculate the forces from the fields rather than directly. Turns out that's a much smarter way to deal with things, because when you think about the propagation of electromagnetic waves, you can either just think about the wave propagating through space as a function of time, or you can think about the charges having a force between each other that's somehow delayed. Delayed in the terms that we think of, where we think about the waves propagating out, and that being the reason for the delay. So the field description has won the day and is the most simple and elegant way of thinking about electromagnetism. The charges and current density generate electric fields and magnetic fields. They propagate and generate forces on other charges and other currents. So all good. Now we need to expand and develop. In the first lecture, we sort of thought about expanding and developing our understanding of the mathematical framework of Maxwell's equations. And you can see that these four equations are written down in terms of the divergence of the electric field and the magnetic field. That's equations 1 and 2. And then the curl of the electric field and the magnetic field. So in terms of memorizing these equations, the left-hand side of these equations should be relatively straightforward. The right-hand side takes a little more thought, and we're going to have a look at that and how they're derived from static laws, or at least steady state laws, in the next few lectures. But in terms of memorizing these things, I'm afraid that just as when you were at high school, you didn't have to memorize F equals ma, but I'm quite sure that you're here at Durham because you knew F. You could write down F equals ma, and you didn't have to look it up. Well, equally when it comes to electromagnetism, my own view, yeah, it's a bit of a dinosaur's view, but nevertheless, my own view is that you need to be able to write Maxwell's four equations down on a blank piece of paper as the sort of building blocks that, or the foundations of everything that goes on top of them. So if you can't do that, stop this review lecture now, grab yourself a piece of paper and just write Maxwell's four equations down. Okay. Having seen that these equations are written down in terms of the divergence and the curl of the vector field E or the vector field B, this naturally leads to some concepts in the mathematics that we use to see what the consequences of these equations are. And one of them is the flux of a vector field. So you know that a vector field, for example, an electric field, is a quantity that has both a direction that it points in and a magnitude. And when we use the phrase vector field, what we mean is we're thinking about a volume in space, and we're thinking about the reality that we can think about the electric field at every point in that space. That makes it a vector field. And that every point, the E field has these two quantities. It's not just like pressure, where it's a scalar quantity. It's a vector field, where at every point in space there's a direction and a magnitude for the vector field. And this naturally leads to the idea of flux. And again, this is one of these quantities where it just occurs repeatedly. It makes some of the understanding more straightforward. And it's defined in terms of the dot product. In simple terms, it's the vector field times an area. Because it's a vector field, we have to define it more carefully than that. And you can see in equation 2.1 that we've defined the flux of the vector field as the vector field dotted with the sum of all the area elements. So we might think about the flux through an open surface like the red one shown at the top of page 2, or a closed surface, which might be the entire surface bounding a volume. And both of these occur in the sort of maths that we look at in this course. We also need these two theorems, Gauss's theorem or the divergence theorem that relates the divergence of a vector field integrated over a volume to the flux of the vector field. That's equation 2.3. And the other theorem is Stokes' theorem, which relates the curl of a vector field integrated over a surface to the line integral of the vector field that bounds that surface. So these are these two important theorems. We looked at them in the examples classes, and I gave some relatively straightforward proofs in the notes for the examples classes. And, you know, we all have our own exam strategy. Mine is very simple. It's you turn up to the lectures, you read the lecture notes, you listen as hard as you can in the lectures and annotate the lecture notes as you're sitting there. Then you reread the lecture notes a few times. Some people rewrite them out. I'm wondering now whether that's really an efficient thing to do, and that if it helps you concentrate on the lecture notes, then that's great. But you could just read the lecture notes, and then it's all about doing questions. If you're struggling with the questions, then I would start with the examples class questions where there are some model solutions, and also then go on to the example class questions where there are no models, where there are model solutions. They're also all on Duo now. And as rapidly as you can, I would leave those behind and go on to the exam questions. If you're struggling with past papers, then go back to the examples class questions, the relevant ones for the particular exam questions you're trying to do. And then concentrating as much as you can on the past papers, try to get yourself into a position where if I made some terrible mistake and reset an exam from last year, and the exam board in the university made such a mistake, that you would get 100% or 95% or something like that. Not 75, 95. So really have a good look at the model solutions and really try and understand them insofar as you can. Okay, the other thing I want to say is that I'm going to make myself available for some questions, but I think that with 250 students in the class and the inefficiencies of electronic communication, it's going to be a tough business. So work with friends. This is physics is a team game. You certainly find that by the time you get on to do a PhD, that it's all about team game. Of course, you have to do your own work. You have to sit down and try and learn the proofs and do the questions for yourself. But if you get stuck, try harder, think different way, think laterally, try and stretch your mind. But if you're completely stuck, go and speak to one of your friends. Speak to one of your friends about physics. I know it's not the sort of thing that was cool to do at school, but You know, you guys are, yeah, what can I say? You're one of the best universities in the world. You should do whatever it takes. Speak to your friends. Say, yeah, let's chat about physics. You talk about everything else. Let's talk about some physics together. And can you help me with this past paper question? So, yeah, I can see that my time here is moving on rapidly. So let me just keep going. So here's the maths, and then we did these differential vector identities. And you'll remember this is 2.5 and 2.6. You'll remember that we need these in order to understand, make a number of manipulations of the maths that allow us to come up with some of the consequences of these four equations for some specific cases. So then we made our way through Maxwell's equations, which in lecture 1 I've just sort of written on the board. And you can see they're differential equations. So they tell us something about how electric and magnetic fields spread through space. We're talking about the gradient of an electric field, or the divergence of electric field, or the curl of a vector field. We're talking about how these vector fields, these E fields and B fields, spread through space as a function of time. So not surprisingly, they lead to waves. But where do they come from? They come from the a careful consideration of the static laws for the electric field and the magnetic field. Now, you know the static laws. We can write down, looking at equation 3.2, we can write down Coulomb's law for the force between two charges, and we can think about those two charges, each of those charges as generating their own electric field. And that leads to an electric field that looks like equation 3.4. Now, we can use that functional form for the electric field to derive Gauss's law, which in its most general form looks like equation 3.10. So this says that we can take the functional form of the electric field and write it down in terms of the flux of that electric field, E dot ds. That's the definition of flux. So the flux of that electric field over a closed surface is just the charge enclosed within that surface divided by epsilon naught. And in this material here, we showed that this isn't just true for a sphere surrounding a point charge, which is trivially true, but it's also true for any bound surface, any complete surface that has charges in it. If we calculate the flux that goes through a surface that has charges inside it, the sum of the flux that goes through the surface equals the sum of all the charges divided by epsilon naught inside that closed surface. Now, if we write Coulomb's law down in this form, then we can use the divergence theorem directly and end up with equation 3.12. And because this is an equation which has volume integrals on both sides, it means the integrand, the bit that's being integrated, is the same on the left-hand side and the right-hand side of equation 3.12. And that leads to equation 3.13, which is Maxwell's first equation. So this tells us something about how the electric field spreads out from a charge. And it's not a surprise, really, that it's built in to the fabric of that equation. We know that how the E field spreads out from a point charge. And not surprisingly, if you manipulate that carefully in the way that we have over these few pages here, we end up with Maxwell's first equation. Then we try to do the same with Maxwell's. Oh, no, we just look at the consequences of that. So you have to think about these curls and divergences, because it's not straightforward to think about what the divergence of a vector field is. And if you think about it entirely in Cartesian coordinates, then you can miss some of the important physical understanding of what this equation means. And I pointed out in the course that if we think about it in terms of spherical polar coordinates, that's equation 3.15, then you can see that the field falls off as 1 over r squared, and it's r to the power 2.00000 off for infinity. And it turns out that the surface area of a sphere also scales as r squared. That's an r to the plus 2, so that's upstairs rather than downstairs. But the fact that in mathematics and in physics we have these behaviors where we have these indices, simple integer powers, is not seen to be a coincidence, and I guess we'll come back to that. So we derived Maxwell's first equation, then we went on to his second equation, which involves the divergence of the magnetic field. In this case, you write down the Biot-Savart law, and we can see what the field looks like outside a straight wire. And then if you look through the mathematics in the way that we do in equations 323 to 326, you can see that if we consider the divergence of an element of current in this straight wire, a divergence of the magnetic field from an element of current, you see that that's zero. And then we can just sum over all the current areas and, current elements. And that leads to Maxwell's second equation, that the divergence of B is zero. So just as Maxwell's first equation comes from Coulomb's law, Maxwell's second equation comes from the Biot-Savart law. And from there we moved on to Maxwell's third equation. Maxwell's third equation comes from Faraday's law. So you'll remember that we can think about inductive electromotive force. We looked at these very simple experiments, and one of them is, these are all done by Faraday. You just have a simple coil of wire, and you have a current passing through it, and you have a loop outside the coil attached to a voltmeter, as shown in figure 1. And you can apply a magnetic field, and of course there's no voltage generated, but if you change the magnetic field, then you get a voltage generated in the way that you saw at high school, you know, using Faraday's law. And what may not have been emphasized at high school, of course, is that the reason you have a voltage across the loop that surrounds the coil is because when that field changes, it generates an electric field. And that electric field drives the charges, provides a force on the charges in this in the loop. And the force on those charges leads to a voltage difference across the loop. And that voltage difference is equal to the rate of change of flux. So this was Faraday's famous experiment and Faraday's famous law. And you can take Faraday's law and you can write it down as V equals d phi dt, where phi is the magnetic flux as shown in equation 5.1. Now, we also considered a motional electromotive force where we took a loop, as shown in figure 3, and pushed the loop down through a magnetic field so that the flux linking the loop increased as time progressed, and calculated the force on the charges in the bottom part of the loop. And again, we find after some algebra that the voltage is essentially the rate of change of flux inside the loop. And we can derive the magnitude of that voltage just using the Lorentz equation as shown in 5.3. And that leads to an equation which is of the form of Faraday's law. So we have this law, Faraday's law, which is true both for inductive voltages, that's the experiment shown in figure 1, and for motional voltages where the loop's moving, as shown in figure 3. And it seems that this is unprecedented in physics, that we have two very different ways of generating essentially the same result. That the physics is quite different, and yet we still end up with V equals d phi by dt. And that's a concern, and of course, as you know, that leads to relativity. Nevertheless, if we take Faraday's law and we rewrite it not in terms of voltage but in terms of electric field, we can manipulate that equation until we get equation 5.10. And just as before, we've got an integral which is of similar form on the left-hand side and the right-hand side. The left-hand side of 5.10 is a surface integral, and so is the right-hand side. And that means that we can conclude that the integrands must be the same, and that gives us 5.11, Maxwell's third equation. So we take Faraday's law. It's a law involving time, unlike Coulomb's law and Ampere's law, and it leads us to this time-dependent equation which is Maxwell's third equation. All right, I numbered them in the order that we considered them. There's no accepted numbering in the literature. So then we looked at deriving Maxwell's fourth equation, and to cut a long story short, we have to consider the idea of a capacitor charging, and rapidly we realized that Ampere's law alone is not going to describe the magnetic field associated with a capacitor charging, that it's simply not general enough, and that if we consider path A, path B, and path C in figure 4, we end up with a different magnetic field for path B if we use Ampere's law in its normal form. Maxwell realized this. He worked out how to fix it. He basically said that the changing electric field associated with the capacitor charging has to be explicitly included in the full generalization of Ampere's law. So if we look at equation 7, in order that we can describe path A, path B, and path C correctly, we have to add this term involving E dot ds in 6.7 to Ampere's law. The first term, B dot dl, the second term, mu naught J dot ds in 6.7 are Ampere's law essentially, and the last term is Maxwell's addition. Okay, if we use the Stokes theorem to re-express equation 6.7, we can write it down as we have in 6.8. Again, in 6.8, there's only surface integrals in every term, and that means the integrands must be equal, and that gives us Maxwell's fourth and final equation. So now we've got Maxwell's 4 equations, and that's all we need. And everything that follows from here is basically involves manipulation and understanding of these 4 equations. So then we start off by looking at what these equations mean in vacuum. And that's straightforward because we can just set the charge density and the current density in vacuum to be 0. Maxwell's 4 equations then become as shown at the bottom of page 4. And from there, we can take the curl of the third equation and use a vector identity in order to get a wave equation, which is what Maxwell did. And as with any wave equation, there's a velocity associated with the waves. And in this case, we find 3 × 10⁸ meters per second for that velocity. Maxwell, of course, realized that that was about the same as velocity of light, and that he reluctantly concluded that light must be an electromagnetic wave, a transverse electromagnetic wave. A number of people had realized that a dimensionality argument meant that mu naught and epsilon naught could be manipulated to give a term in terms of meters per second that was similar to velocity of light. But Maxwell was the first to add this additional term to Ampere's law, combine the equations in a way that meant that he could give a mathematical description of electromagnetic waves as transverse waves. So let's be just clear about what a transverse wave is at this point. If you think about a wave that's traveling from your computer screen to your eyes, it's traveling in a direction associated with the propagation of light. But of course, the E fields and B fields are pointing in a direction that's parallel to the screen you're looking at. So even though the wave is propagating in a direction associated with a vector that points towards your eyes, the vector associated with the E field and B field is orthogonal to that. And that's important to realize when we come to more complicated things. We need to make sure we've got that simple idea clearly in our minds. And that means that when we write down the solution to equation 7.6, which is for B fields, you've got to remember that when we write one of the possible solutions, which is shown in equation 7.8, the K vector points in the direction of propagation, but the polarization term, the B naught in equation 7.8, points in a direction that's orthogonal to K. And you have to keep that in mind when we start manipulating these equations, when we're talking about the propagation of a transverse electromagnetic wave. So we can just continue this process. We've now got the velocity of these electromagnetic waves in vacuum. we use Maxwell's equations on through until equation 713, 712, 713, and we find that the E fields, the B fields, and the direction of propagation are all perpendicular to each other. The B field's a factor of C smaller than E. This is written down just above figure 5. And E cross B is in the direction of K and gives the direction of propagation. That's in vacuum. More generally, as you know, later on in the course, we see E cross H is the direction of K. Okay, and there's a pictorial representation of the electromagnetic wave. We found these waves by taking the curl of either the third equation or the fourth equation. We can also take the divergence of the fourth equation, which is what we've done in equation 814, and then you end up with equation 817, which is the differential continuity equation. If you integrate both sides over a closed surface and then use the divergence theorem, you realize that equation 817 is an equation that says that if we consider a closed surface with charge inside it, when charge leaves, when the charge inside that closed surface reduces, it must pass through the surface itself. So if we have a closed surface, the charge inside reduces, it must leave through the surface. In other words, that if you require that Maxwell's equations hold at every point in space and time, then we have conservation of charge. Okay, so all good. Built into the fabric of Maxwell's equations is charge continuity. Then we went on to look at relativity. It's a very simple experiment, and we can set up one of many experiments. And I think that part of the thing that you have to appreciate when you look at this this material here is that there are many possible experiments that we can set up, and all we're doing in this these few lectures here is considering one possible experiment. This is the experiment that you might do in the lab, where if you were trying to test Ampere's law, you would take a wire, you would connect it to a power supply, you'd put some current through the wire, and you would measure the magnetic field associated with that current passing through the wire. That's the experiment that you or I could do, and it would be quite a reasonable experiment and a good experiment if we were testing Ampere's law. Now, we could set that experiment up in a number of ways. One of the ways that we could set it up is we could make sure, and this is usually the case when you connect a wire to a power supply, that the wire itself didn't have any net charge. So, you know, we've got a situation where we can just test Ampere's law in that sort of way, and then we can do a thought experiment. Now, you may ask, why is the wire net charge neutral? It need not be. But that's the way we set the experiment up. Now, if we then do the thought experiment where we jump onto the moving charges in the wire and apply Maxwell's equations again, this is where the complication arises. And this is what's going on in figure 6 and figure 7. Figure 6 is the experiment that you or I would do, where we're just putting a current through a charge, putting a current through a wire. And in this case, we've got a stationary charge outside the wire, and we know that if the charge is stationary, there's no force on that charge, so the charge stays where it is. Then in the second case, if we jump onto the negative charges, now the positive charges in the wire that appear to be moving, and the positive charge that's outside the wire, that's stationary with respect to the positive charges inside the wire, also appears to be moving with the same velocity. That's shown in figure 7. And all you have to do is apply Maxwell's equations to these two circumstances and decide whether or not the charge moves into the wire. And if you just insist on classical or Galilean transformations, and you just have the apply Maxwell's equations, I'm afraid in one case, the guy sitting in one frame, where the positive charge outside the wire is stationary, doesn't see the charge moving. In the second case, the charge crashes into the wire. So at that point, given that in standard classical physics, we can't get, I mean, physics is only predictive. Well, yeah, I'm stumbling over my words here. We can't have physics where if we apply it in one frame, we get one result. But if we go into another perfectly reasonable frame, in other words, if we ask another scientist to do the same experiment who doesn't sit in the same frame that we do, and they get different results or predict different results, then these mathematical predictions are worthless. We have to be sure that they agree and I agree about what happens, whether or not this charge crashes into the wire, because we can do the experiment and see whether or not the charge crashes into the wire. And if one of us has applied, quote unquote, the laws of physics and it's the wrong prediction, then we have to throw those equations out. So, given that these two frames lead using Maxwell's equations and Galilean physics to contradictory results, we have two possibilities. We can either throw out Maxwell's equations, or we can throw out our ideas of absolute space and absolute time. And you know, because you've done the course, that what we did was threw out our concepts of absolute space and absolute time. And what you have to do is make sure that you understood the idea of a proper frame in special relativity. You ask, when you measure the distance between charges, you have to make sure that those charges are stationary when you're measuring the distance between them. If they're moving, you have to appreciate that Einstein tells us that you're going to measure a Lorentz contracted distance. So we just think about the two frames, we apply the Lorentz contraction, and we realize that in both frames, we get the same thing happening. We get the charge crashing into the wire if we set it up in a certain way, if we set up a certain experiment. Equally, we can set up other experiments where the charge doesn't crash into the wire. But what we have to be sure of is that in both frames, the charge doesn't crash into the wire. So now we apply Maxwell's equations with the Einstein transformations for space and time, and we can both agree and both predict what happens to the charge. And then we're in the realms of physics with strong predictive power. So that's where we found that all of special relativity is built into the framework of Maxwell's equations, and it's then not a surprise that Einstein talks about the speed of light as being the constant for the universe, because of course all of these ideas come from Maxwell's equations. Then we had some hard miles to do, because we want to understand how materials behave when they're exposed to electromagnetic waves or changing electric fields and magnetic fields. And that means we need to understand the basic properties of materials. And in the next few lectures, we looked at these core classes of materials. First of all, we looked at conducting and superconducting materials. You've looked at conducting materials yourself at high school long ago, so you've got quite a good mathematical and physical feeling for what a highly conducting material is and a highly resistive or insulating material is. You've got a mathematical description through Ohm's law. You've got a physical description in terms of either the scattering length or the scattering time or the number of charge carriers. So you know from Ohm's law that if you've got something that's highly resistive like glass, then the number of carriers is extremely small, or maybe the scattering time for the carriers that are there is extremely short. And you know for a highly conducting material like copper, then the resistance is low, the resistivity, equivalent resistivity is low, and that means that we've got a large number of carriers that aren't scattering very much as they're making their way through the conductor. So you've got this mathematical description through resistance or resistivity. You've got this physical understanding through the Drude model, which gives you this expression for the resistivity in terms of microscopic parameters. You've got a physical understanding of what these microscopic parameters are. You have some idea that if you apply an electric field or a voltage across a resistor or an electric field across a resistivity, you accelerate the charges, they scatter, they lose their velocity instantaneously, and then they re-accelerate again. So you have all the mathematical tools to understand conducting materials, and I just ran through those and put them all together in one place so that you could see the structure of these things. Equation 9.1 is what you learn probably for GCSE. Then we can write down things that are intensive variables like resistivity or conductivity, which are essentially derived from Ohm's law. Then we can think about the Drude model in terms of scattering time, and that leads to an equation like equation 914. Now, if we're applying not a DC voltage, but an AC voltage, not a DC electric field, but an AC electric field, then we have to take account of the fact that the current that's produced as a response to that AC voltage or AC electric field may not be in phase with the driving voltage or electric field. And therefore, if we want to describe these things mathematically in detail, we can either do that using sines and cosines and have a whole lot of trigonometric relations, or we can introduce this idea of complex resistivity or complex conductivity. And we as scientists need to know how to manipulate a complex conductivity and how we can use it to calculate the current that's in phase and out of phase as a response to a voltage. So if we've got a voltage which is described by a cosine term, then we may have a current that's described by a cosine term and some current that's described by a sine term. And we can either use that, we can either find those terms using trigonometric relations, or we can find those terms using complex numbers. And in this course, we use complex numbers because as we get to more complicated systems, complex numbers becomes a much more elegant way of doing it. So that's that completed the work on conductivity, and or at least the work that you would have essentially completed at high school and in the first year. And then we need to go on from thinking about circuits to thinking about the propagation of waves. And we thought about dispersive waves and ballistic waves. And the conclusions that we need are here in equations 928 to 931, where at high school you saw V equals F lambda, which can be written as omega over K real. That's the phase velocity, so that if we have an infinite plane wave with just one wavelength or just one frequency, we can write down the velocity of that plane wave in terms of F lambda or omega over K real. Also, we can talk about the group velocity of a packet of waves. So that if we have a packet of waves with a range of frequencies or a range of wavelengths that give us this packet, then we can talk about the peak in this packet of waves, maybe, for example, a ripple on a pond, moving across the pond at a certain velocity. It's the characteristic velocity of all the plane waves that go to make up that pulse or that packet. And that velocity is d omega dk. Of course, it's got the same units as omega over k, and it's just the differential of omega with respect to k real. Then we can look at the double differential. If it's zero, the wave moves ballistically. That means it moves like a ball, which means that the wave doesn't change shape as it propagates through space as a function of time. If d2 omega dk real squared is not zero, then it means it spreads out. And typically a wave, for example, a ripple on a pond does spread out, so it moves dispersively. A soliton, on the other hand, doesn't spread out and therefore keeps its shape. Of course, a ball or a bullet doesn't spread out as it moves through space as a function of time, so they move ballistically, which is where the word comes from. So we've understood how to identify the properties of waves from the dispersion relation, which by definition is a relationship between omega and k. And I obviously need to move on with this a little bit. So from here, we thought about the propagation, applying Maxwell's equations to a conducting medium. And you can see that we now have to add in the fact that if you've got an electromagnetic wave propagating through a conducting medium, the electric field is going to generate a current density inside the conducting medium. And that current density has to be explicitly included in Maxwell's four general equations in order to describe the electromagnetic wave in a conducting medium as it propagates through that material. So unlike the case for the vacuum where we could set mu naught J to be 0, we have to use Ohm's law and substitute in for mu naught J using the conductivity of the conducting material. And then we end up with a wave equation like 935, where we have this additional term in dE dt coming from the fact that the conductivity is not 0, which it was in a vacuum. So now we've got a more complicated wave equation to solve. It's 937, but you know how to do that. You just take the plane wave solution, 938, substitute into the wave equation. That gives us the dispersion relation, which is the relationship between omega and k. And then we can just calculate all the properties of those waves, given that we've got the dispersion relation. We can get the phase velocity from omega over k, the group velocity from d omega dk, and from d2 omega dk squared. If it's 0, it's moving ballistically, and if it's not, it's moving dispersively. And that gives us all we need. And then if we want to calculate more explicitly how the wave decays as it goes through the conducting material, we take equation 939, which is the relationship between omega and k, and substitute an expression for k back into equation 938. Now, in this case, 939 is not written in a very straightforward way for us because it's given us an expression for k squared in terms of a complex number, which has both real and imaginary parts. So we have to find the square root of this complex number. And in the case of a highly conducting material, that's very easy to do. That's just equation 944. In general, it's more complicated. There's some algebra that you have to do using the Argand diagram, and that's explained in one of the examples classes. So you take 939. As scientists, we need to be able to find the square root of a complex number. Please check that explicitly if you want to do calculations and get them correct. And then you just substitute the expression you've got for k back into equation 938, and that leads to equation 945. And if you haven't done it, and I encouraged everyone in the examples classes to write these equations down, you should write down equations 945, 46, 947, and you can see that you end up in 946 with a wave equation and with a decaying part. So the wave part is the cosine part, and the decaying part is the exponentially decaying part at the end of 946. So now we know how a wave propagates through a conducting material. As the wave comes in, the E field drives current, that generates heat, that loses energy. That means that energy is lost from the wave to produce the heat, and the wave decays. The magnitude of the transverse electric field and magnetic fields decay, and the E field slowly decays exponentially as it propagates in through the metal. So we get all from the mathematics, of course, we get all the physics of what's going on. From there, we also looked at electromagnetic waves propagating through plasmas. And in this case, we again derived the dispersion relation. We found that there were two distinct regimes for the velocity of waves passing through a plasma, as you can see in, I'm afraid the figure's not numbered on page 7. And you can see that below the characteristic frequency for the plasma, the wave decays, and above that frequency, the phase velocity of any plane wave is faster than the speed of light, but the group velocity, which is the velocity with which any information is propagates, is smaller than the speed of light as required by relativity. And we can see that there are some equivalent data looking at the reflectance of metals that shows this sort of cutoff frequency. So not surprisingly, there's a lot of experimental evidence supporting this very simple description of how electromagnetic waves propagate through simple metals. It's not perfect, as we can see at the top of page 8, but still very good. From then we went to look at superconducting materials, and we derived the two London equations. That's equation 956 and 957. And the important thing to realize here is that this leads to zero resistance for superconducting materials and to the Meissner state. And the Meissner state is is a special state for superconducting materials because it's associated with DC magnetic fields. So you know that if you applied a DC magnetic field to a normal metal like copper or silver or gold, the field would just penetrate into the superconductor. However, in the case of penetrate into the metal. However, in the case of superconductors, if you apply a DC magnetic field, the static steady state condition is that the currents are produced at the surface of that superconductor that screen out that applied magnetic field. And that's almost unique to superconducting materials. And it means that if we applied a slowly changing AC magnetic field, that those currents would change and would continuously screen out an AC magnetic field, even though if we were producing that field at low frequency, in the case of a simple metal like copper or silver or gold, that AC field would just penetrate through the whole of the material, and the field inside and outside of the metal would be the same. In the case of the superconductor, the net field inside the superconductor is zero, or at least very close to zero. So we looked at where the London equations went for, and that completed the work on conducting and superconducting materials. Having done that for conducting materials, we then looked at the next important class of materials, which is dielectrics. We looked at polar and non-polar dielectrics. And just as we looked at the Drude model, we looked at the equivalent framework for dielectric materials. In the case of dielectric materials, you apply an electric field. There's some charge separation that occurs within the dielectric, and that leads to a second electric field produced by the material. And we defined, as you can see here on pages 2 and 3, the fundamental response. So we characterize what's going on at the microscopic level in 10.1. We characterize the equivalent for per unit volume in 10.2. And then we characterize the strength of the response, how large this second electric field is in equations 10.3 or 10.4. They're essentially describing the same sort of thing, and the permittivity or the electric susceptibility are a matter of taste or choice used by one community or another within science. Okay, once we've got the basic building blocks, we've got the sort of what's going on at the microscopic level, we can then start calculating what happens if we polarize an electric field, and what are the charges and current densities that are produced for a given polarization found in a material as a response to an applied electric field. And the derivation of the charge density is completed by equation 10.11. And from there, we can calculate the current density, that's in 10.13. And we can also calculate the response of a dielectric to an AC field. So the important thing here is that we've now got, if we've got a material with a certain permittivity, we know that if we apply an electric field or a changing electric field to a dielectric material, we know the charges that are produced and the current density that's produced everywhere. Just as with a conducting material, we can apply an electric field or a changing electric field, for example, associated with a transverse wave, and we can calculate the current density that's produced. And using this sort of mathematical framework, we can now self-consistently use Maxwell's equations, where we can substitute in for the current density and the charge density under any circumstances, and that allows us to calculate what happens to waves, for example, as they pass through these classes of materials. We also introduced this idea of an auxiliary field. I'll let you have a look at that. And finally, we went on to magnetic materials. It's just the same sort of structure. We think about what's going on at the microscopic level. That gives us equations 11.1, 11.2. Then, having set up the framework for the way a magnetic material responds, we calculate the current density associated with a magnetized piece of material. If you take a magnetic material that's of cylindrical shape, apply a magnetic field and magnetize the material, the current only flows around. If it's uniformly magnetized, the net current is only around the surface of the cylinder. If you've got a magnetization that's varying spatially in the material, you can end up with a current density, and that leads to equation 1110. Once we've got the bulk current density, we can also calculate the surface current density, or the current per unit length. That's 1115. And now we're home. We've got the current densities associated with magnetic materials. So this allows us to, we now know what charge densities, what current densities are produced in all the important classes of material. So from here, we also looked at this auxiliary field H, and I'll ask you to have a look at that. But now we can think about a wave propagating through space and penetrating into a material that could be conducting, it could be a dielectric, it could be magnetic, and we can calculate what happens. All we need to do is make sure that when we've written Maxwell's equations down in their most general form, we include all the current density and all the charge densities that's produced as a result of the different properties of these materials. And that leads in the end to the wave equation and the dispersion relation for such a material. The maths, the algebra is certainly more complicated. The maths is almost the same as we had for a vacuum. All you do is you take the curl of either the third equation or the fourth equation, and that leads to a divergence. That leads to a wave equation. So here's the fourth equation here, equation 12.8, which is written down now where we've substituted in for J all the current density that can be produced from a conducting material, that's the sigma NE term in 12.8, dielectric material, that's dPdt, and magnetic material, that's curl of N. So now we've got all the current density that's produced, and this can be rearranged, and then we substitute in, let me just see what we've done here. This is Maxwell's fourth equation. And then we've taken Maxwell's fourth equation and substituted it into the curl of Maxwell's third equation. We can either do it that way around or the other way around. We take either the curl of the third or the curl of the fourth and substitute in the other equation. So that gives us equation 1213, and that leads to the wave equation, the general wave equation of 1215. If we if we don't take the curl of the third equation, we take the curl of the fourth equation, we get equation 1216, the wave equation for a magnetic field. And then once we've got the wave equation, we know how to, we did this for a vacuum, we know how to calculate all the properties associated with waves propagating in this medium described by this wave equation. We just take the plane wave equation, equation 1217, substitute into the wave equation itself. This gives us the dispersion relation, which is written in terms of k squared. We need to be smart and take the square root of this complex equation to get k. We substitute k back into the plane wave equation or plane wave solution, 1217, and then that gives us equation halfway down page 15, which is the electric field in terms of space and time. And from there, we get the wave equation shown here, and that gives us a wave part and an exponential part, and we can therefore calculate how the wave propagates through the material from the wave part and how the E field and the associated B field decay as it makes its way through the material. So now we can, we've looked at all the important classes of materials, and we can calculate all the we can calculate how electromagnetic waves propagate through any of these materials. Now, the fact that these waves are decaying naturally leads to some ideas about energy and power and this sort of thing. And this is where the Poynting vector comes in. And you can see here that we assumed that the Poynting vector is correct and showed that it was consistent with conservation of energy. Other textbooks, you start with the conservation of energy and show that that means that you have to interpret E cross H as the Poynting vector, where the Poynting vector is the instantaneous power per unit wave, per unit area associated with an electromagnetic wave. So we did it this way round, and you can see that we end up with this very nice equation at the bottom of page 1, which is a self-consistent statement of the conservation of energy. Okay, and we're going to need that because we're going to go on to think about production and transmission of electromagnetic waves. Now, in thinking about the production of electromagnetic waves, radiation and communication, we need to think about what sort of entity are we going to introduce as producing electromagnetic waves. And there are two simple entities or building blocks from which everything else can be constructed. One is a Hertzian dipole, which is just two charges, positive and negative charges, oscillating back and forward past each other, or should one strictly say through each other, if that's possible. And then the second is you can think about a loop where the current in that loop oscillates one way and then flows one way and then flows the other way in a sort of oscillation, in a sort of oscillatory current. We considered the Hertzian dipole, and the most simple way to calculate the fields generated by a Hertzian dipole is to use these idea of potentials. So we rewrite Maxwell's equations in terms of potentials. And without going through all the details, you can see that we can rewrite Maxwell's equations as shown as, I guess it's 318 and 319. It means that if we can solve equation 318 and 319 for the potentials for V and for A, we can then calculate the equivalent E fields and B fields. So this has the advantage that instead of solving four equations, Maxwell's four equations, we can solve these two equations, which are written in a form, an equivalent general form in terms of wave equations, which means they naturally lead us to a more straightforward and elegant way of finding wave equation solutions. But the problem is that they're, of course, not direct. We calculate these things in terms of potentials, and then we have to convert into electric and magnetic fields. So we can either write down Maxwell's four equations, or we can write down these two wave-like equations for potentials V and magnetic vector potential A, 1318 and 1319. And that's exactly what we do. We start off by trying to solve equation 1319. And I provided some justification for the solution. First of all, by considering part of the equation, ignoring the temporal part, and writing down a static solution, and then thinking how we might generalize it. And if you were persuaded by that, that's great. And it's certainly a standard tool in mathematics as a way of finding solutions. If you weren't persuaded, then we just take the solution, which is given by 1325, and just substitute into the wave equation for A, 1319, and see that it is indeed a solution. And then once we've got the magnetic vector potential, we know from the definition of that magnetic potential how to calculate the magnetic field. And if we've got the magnetic field, we can calculate the electric field from one of Maxwell's equations. And that's exactly what we do for the Hertzian dipole. And we end up with solutions that are quite complicated for the B field and the E field associated with the Hertzian dipole. But we can look at near field, what happens close to the Hertzian dipole, and far field. That means what happens a long distance from the Hertzian dipole. And this means we lose some terms that are only important in second order under relevant approximations. And in particular, if we look at far field, we get these very nice plane waves propagated out from the Hertzian dipole in the plane of the dipole itself. And we have this idea that we have this language that we develop, we have this language that developed that has a Hertzian dipole at the origin, and we can think about a sphere surrounding the Hertzian dipole at the origin, and we can think about the E field that's produced in a direction in the equatorial plane, or maybe the E field that's produced in a direction associated with going north through the North Pole, or at some angle to the North Pole. So this is the way that we use scientific English words, but of course it's all there in equation 1332. What the E field looks like as a function of the direction it points in, that comes from the theta vector, and the angular dependence of the magnitude of the E field, that comes from the sine theta term and the prefactor, and the velocity comes from the sine kr minus omega t term. So we have to look at an equation like that. That's just the far field That's the important term in the far field when you're a long distance from the dipole, and it tells us what the magnitude of the E field is in the equatorial plane, in fact, in any direction at all. And we can plot that using polar plots or using standard plots. And then we can think about physically what happens and how do you end up with these planar waves out at distance. What goes on near field and what goes on far field, and that's shown in figure 4, and we talked about that, and there's some visualization and a link that you can see there that's on the web that actually a very good student who worked with me in his 4th year produced these really beautiful visualizations. So then we can think about the energy associated with these fields. And of course, this naturally means we go back to the pointing vector. And you just have to be a little bit careful when we think about energy or power, whether you're talking about the instantaneous power that's passing through a certain area, or whether or not you're thinking about the instantaneous power that's passing through a sphere that surrounds a Hertzian dipole, or whether you're thinking about the total power that's passing through the sphere, not the angular dependence of that power per unit area, but maybe the total power. So we have to be careful when we ask questions using scientific words about exactly what mathematics we're asking for. So be careful about that, but all good. Then we come on to Pauli, of course. Pauli's famous God made the bulk, but the devil has the surfaces. Now we have to think about how electromagnetic waves cross interfaces. And of course, you know, as physicists, we don't like to think about interfaces very much because we don't understand them, basically. But this is a very useful start, and I need to give this some more thought. But anyway, in terms of passing exams, this is the material that you need to know. We need to understand how electromagnetic waves pass from air through glass, or maybe pass from air into water, or from water into air. And this means we need to understand what happens at the interface. How does the wave continue propagating? How does it change as it goes from one material to another? More specifically, how does it change the direction? So you know that this leads to incredibly beautiful things like rainbows, for example, where the way that the light interacts with the droplet of rainwater means that we get these incredibly beautiful rainbows of biblical literally of biblical proportions, and explains why you can see through some panes of glass if you're looking at them face on, but you can't see through them if you're at some angle, and explains why we have polarized glasses. And we talked about this in the examples classes, and there's a whole series of questions there. So we have to think about how an electric field changes as it passes through from one material to another, and we do that by thinking about a DC electric field. So these arrows shown in this figure I emphasize in the lectures are DC electric fields, and they change direction. And we use Maxwell's equations by thinking about either the cylinder or this path in order to calculate what happens to the direction of the E field as you go from one dielectric to another, or from vacuum to a dielectric, for example. And that leads to these results here, that E parallel to the interface is conserved, and D orthogonal to the interface is conserved. So we can think about, and you can see it's written here, that if we look at figure 1 on the right hand side, there's the E field in medium 1, E1, and in medium 2, E2, and you can see that the E field parallel to the interface is the same for E1 and E2, but the E field orthogonal to the interface depends on the dielectric constant. And that's what we derive by considering these two configurations, by insisting Maxwell's equations hold on any length scale. And then we do the same for magnetic field. And you can see in figure 2 and equation 1412 that the B field orthogonal to the interface and the H field parallel to the interface are continuous across the boundary, and that's represented pictorially on the right hand side of figure 2. Those were static derivations that were true at a point in time for a static E field and B field. But of course, if we fire an electromagnetic wave across an interface, the assumption is that Maxwell's equations are true on any time frame at every point in time. And therefore, those conditions have to be met by the E fields and B fields of an electromagnetic wave as they propagate from one material to another. And that leads to all the laws of optics, to the 3 laws of optics shown in 1427, 1431, and 1434, or the words below that. So all the laws of optics hold, and you just got to be a little bit careful. Students often make the mistake of not being clear about the plane of incidence and the interfacial plane. If we look at figure 4, the interfacial plane, as the name suggests, is the plane at the interface between medium 1, in this case medium 1 and medium 2, and that plane comes out of your computer screen. The plane of incidence is the plane in which the k vectors exist. That's the plane of your computer screen. Okay, once you've sorted that out and you apply the equations in the right way, you get the 3 laws of optics. And then if we think about applying those continuity equations and think about the magnitude of the E field that's transmitted and reflected for an incident wave, we end up with Fresnel's 4 equations. One for the E field normal to the plane of incidence, that's equations 2, there are 4 equations in total. 4 equations in total, 2 for each polarization. So for each polarization, we can think about the fraction of E field that's reflected and the fraction of E field that's transmitted. That's 1441 and 1442. And then we can think about the E field parallel to the plane of incidence. Be careful. The boundary conditions are associated with the interfacial plane. The 2 polarizations are associated with the plane of incidence. So be careful about that. And that leads to Fresnel's other 2 equations. And we can plot them as shown in figure 7. And that leads to all the beautiful things that I've mentioned in terms of rainbows and Polaroid glasses and light and so on. And there are a huge number of questions that you could ask to test whether you understand Fresnel's equations, and those are in the examples classes and in the past papers. So this was a more general, more detailed description of the lecture material, and that I provided because I was worried that I wouldn't complete everything in the last lecture. So here we are, and we come to the coefficients of reflection and transmission, and that's covered for highly conducting materials. And not surprisingly, you find that for highly conducting materials, the most of the electromagnetic wave is reflected, which is the origin of things like mirrors. And then the last topic we looked at was waveguides. Waveguides are in principle very simple things. They're just tubes of metal. They're not always tubes of metal, but we can think about the most simple case first. Tubes of metal, it's shown in figure 11. And there are only certain waves that can propagate down tubes of metal without generating heat or inducing currents in the walls, in the tube, in the metal itself. And those waves that can propagate along waveguides propagate without any dissipation, and therefore can propagate for kilometers, and are the basis of fiber technology and the internet. Okay, the fibers, of course, are glass rather than metals, but the maths you'll see is the same, and we've essentially limited ourselves in the lectures, but not in the examples classes, to tubes as metals as a description of waveguides. And we can realize that inside the tube, the medium is basically air or vacuum, and we've just got to solve equation 515 with the boundary condition that there can't be any electric fields generating currents in the walls of the waveguides. So we can write down an equation like 15.2, and then we can look at the constraints on the parameters in 15.2, and we find that as with plasmas, there's a cutoff frequency below which you can't propagate a wave of this type through a waveguide. And we can also calculate the nature of the B field associated with this type of wave. And although the E field is orthogonal to the axis of the waveguide, the B field has a component that's both orthogonal to the axis and parallel to the axis. This means it's not a transverse electromagnetic wave anymore. It's a transverse electric wave, but the B field isn't orthogonal to the axis of the waveguide, and so we call it a transverse electric wave rather than transverse electromagnetic wave. And equally, one can calculate a transverse magnetic wave where the B field is orthogonal to the axis of the waveguide, and the E field has a component that's both orthogonal and points along the axis of the waveguide. So we find a completely different type of wave that propagates through waveguides. They're known as transverse electric and transverse magnetic waves. Of course, they obey Maxwell's equations, and they propagate without generating any current or heat in the waveguide. Well, I hope you've enjoyed the course. Do your best, work hard, work as hard as you reasonably can, and look forward to a more relaxing time when the exams are done. You're in a great university, and you just do the best you can because you know that's the smart thing to do. Thanks a lot. I wish you luck, and I'm hoping that I can, and I'm going to sign off. All right. Thanks very much. Bye.